All right. So tonight, in our session, we're going to focus on some of the concepts behind our carbohydrate chemistry. So one of the things that you probably noticed in terms of the discussion of carbohydrates is that if we really didn't know a lot about the basic organic functional groups, especially your alcohols, your aldehydes, and your ketones, you really couldn't have much of a discussion about carbohydrates. And we'll get into that tonight, especially in terms of the discussion of monosaccharides and such like that. But one of the things I want to sort of talk about first, which will lead into our discussion of carbohydrates, is I want to talk a little bit about chiral carbons. I want to talk
Mhm.
a little bit about chiral compounds. And then I also want to talk a little bit about what are known as enantiomers. Okay. So essentially, when you have a chiral compound, you have essentially, it doesn't have to necessarily be an organic compound. It could actually be an object or something like that. But I guess for our purposes, the organic compound does not have a plane of symmetry in its structure. So what essentially is a plane of symmetry? A plane of symmetry is a plane that would cut through the compound, its structure, so that the two halves produced would be mirror images of each other. If your organic compound in any form of its structure does not have a plane of symmetry, then the organic compound is deemed to be chiral. So what does this mean? Well, it means that not only is the version you are looking at exists, but there is also a non-superimposable mirror image that exists as well. And essentially, these two structures are what are known as enantiomers of each other. In other words, these two structures not only have the same chemical formula, they also have the same connectivity, but they are two non-superimposable mirror images of each other. So this type of isomerism between structures is what is known as enantiomers. And as you saw in the chapter, and as we'll get into again this evening, this form of isomerism is really prevalent in monosaccharides and, in a sense, in carbohydrates in general. Now, as we talked about in the slides, a practical example of enantiomers are your hands. Your left hand and your right hand are enantiomers of each other. Because if you think about it, if you take your left hand, there's no plane of symmetry that exists in your left hand. No matter how I cut it, the two halves would not be mirror images of each other. So what does it mean? It means that somewhere out there, there's a non-superimposable mirror image that exists as well. Here it is. And you're probably seeing, you might be seeing it in a different way, but this, I'm holding up my right hand. So they are mirror images. And if I were to hold my left hand up to a mirror, I would see my right hand. If I were to take my right hand and take it out of the mirror and try to superimpose it, remember, this would not be superimposing because one palm is down, the other palm is up. At closest, this would be superimposing. And you can tell from the video, and what we talked about as well, that my fingers would not line up. So they are same chemical formula, same connectivity. They are non-superimposable mirror images. So what's their relationship? They are enantiomers of each other. Now, one of the good things about telling whether an organic compound is chiral or not is that we don't necessarily have to go looking for planes of symmetry. It turns out that an organic compound is usually chiral if it contains at least one chiral carbon. Now, the reason why I say usually is because there are actually examples, and we won't go into it in this course, but there are actually examples of organic compounds that have 2 or more chiral carbons, but yet have a plane of symmetry. So they would not be chiral, as we'll mention towards the end of this part of our discussion, they would be achiral. But let me be clear, for our purposes and for this course, if you find one chiral carbon, you can definitely assume that the organic compound is chiral. Okay. And in reality, it turns out if you have one chiral carbon, the organic compound is always going to be chiral because there is never a plane of symmetry. Now, what defines a chiral carbon? It's a carbon that has 4 different atoms or groups of atoms attached to it. Okay, so it has 4 different atoms or groups of atoms attached to it. And that's what defines a carbon as being chiral. So for our purposes and for this course, if we find one of those, and we're going to do some examples in a moment, you could assume that the compound is chiral. And what that also means is not only is that version you're looking at exists, but there's also a non-superimposable mirror image that also exists. What's the relationship between them? They are enantiomers of each other. Okay. Again, as always, if you have any questions, feel free to unmute or use the chat to jump in. All right. So let's actually take a look at a couple of examples in terms of finding chiral carbons. Okay. So just to mention a couple of, well, maybe we'll talk about some shortcuts. We'll talk about some shortcuts as we go along. So basically, when you're looking for chiral carbons, what you really have to do is you really basically have to take one carbon at a time, and you have to essentially see what are the 4 things attached to that carbon. Are they truly different? And if the answer is yes, then that carbon is chiral. If they're not totally different, then that carbon is not chiral, right? So this was a pretty straightforward example. If we take a look at the first carbon to the left over here, the 4 things attached to it would be chlorine at the top, hydrogen to the left, chlorine to the bottom, and essentially the entire right portion of the structure. Is that 4 different atoms or groups of atoms? And the answer is no. So the carbon on the left is not chiral. Okay. If we take a look at this structure here, this carbon over here to the right, sorry, what are the 4 things that are attached to it? You've got chlorine, you've got OH, you've got hydrogen, and you've got the entire left portion. Is that carbon chiral? And the answer is yes. Okay, so the carbon to the right there would be a chiral carbon. So what does this mean? It means that this compound is chiral.
Can I just ask a question?
Of course, go right ahead.
Sorry. So for that first one, I got it right, but I'm not clear why, because there's chlorine on both tops of the carbons.
Okay, so
So,
that's okay. So let me go back for a second.
okay.
So for the carbon on the left, the reason why it's not chiral is because it has 2 chlorines attached to it. So when you're doing this, you're looking at the carbons individually. You're taking them separately. They're sort of independent of each other.
Okay.
Now, for the carbon on the right, if I was going to box in the 4 things attached to it, it would be chlorine,
Mhm.
OH, H, and then the entire left portion. So if you look at what I boxed in, are those 4 different atoms or groups of atoms? And the answer is yes. Cl, OH, H, and this, however you want to call it, a carbon with 2 chlorines and a hydrogen. Those are 4 different atoms or groups of atoms. So that
Okay.
carbon would be chiral.
Got it. Okay. So that's like an entity of itself. Like,
Yeah, as I said, you really want to take each carbon individually
mhm,
and see what the 4 things are attached. So it doesn't matter in this case that both of those carbons have chlorines. If you look at the carbon to the right, it's got 4 different groups attached to it, where the carbon on the left, because it has a chlorine here and a chlorine there, it
mhm.
can't be chiral.
Okay. Thank you.
Of course. Other questions? All right. So here's our next example. Okay. So couple hints, couple shortcuts in terms of finding chiral carbons. CH3 carbons and CH2 carbons can never be chiral. Think about why that is. If you're a CH3, if your carbon is a CH3, that means you have 3 hydrogens attached to that carbon. So that can't be 4 different atoms or groups of atoms. So CH3s, those carbons are never chiral. Along similar lines, CH2s can never be chiral because 2 of the things attached to the carbon would be hydrogens. So that can't be 4 different atoms or groups of atoms. So basically what that means for this example is that the only carbon that we really have to look at, once you understand sort of the shortcut here, the only carbon that really comes into question is that carbon right there, the CH carbon. It's sort of in the middle. So then, okay, what are the 4 different atoms or groups of atoms attached to that carbon? It would be the bromine, the hydrogen. Now, one of the common mistakes students would make with this question is that they say, oh, it's a carbon to the left and a carbon to the right. So that's exactly the same. But remember, it's 4 different atoms or groups of atoms. So if I was going to box in here, one group would be the entire left portion. The other group would be the entire right portion. So if you look at it that way, are the groups on the left and the right different? And the answer is yes. This group to the left is CH2CH3. This group to the right is CH2CH2CH3. Those are different groups. So in fact, that carbon in the middle there is chiral. All right. So I like that example because it illustrates that aspect. Just want to take a look at one more to illustrate one other point. Okay. So in this example here, we can rule out a lot of carbons very quickly. We can rule out all the CH3 carbons because as we just talked about, CH3 carbons and CH2 carbons can never be chiral. So basically what that leaves us with are the carbons in the double bond. And it turns out that carbons in a double bond and along similar lines, carbons in a triple bond can never be chiral as well. Why? Because the idea for a chiral carbon is to have 4 different atoms or groups of atoms attached to you. If you're in a double bond, in essence, what's the maximum number of different things you could have attached to you? It's actually not 4, it's only 3. And if your carbon's in a triple bond, the maximum number of different things that can be attached to you is not 4, it's actually not even 3, it's only 2. So carbon atoms in a double bond or triple bond can never be chiral. So this particular example here has no chiral carbons. And therefore, it's what is known as an achiral compound. Essentially, an achiral compound is a compound that's not chiral. Why? Because in essence, if we were actually to make a model of this structure, you would actually have a plane of symmetry that would be present. So this particular compound has no chiral carbons associated with it and would have a plane of symmetry in a sense. The object and the mirror image would essentially be the same. They wouldn't be enantiomers of each other. They would actually be the same. All right. So the nice part about this is that we don't have to go looking for planes of symmetry. The chiral carbons are usually a pretty good predictor. And for our purposes, for our course, if you find one, the compound is going to be chiral. If you don't find one, then the compound is going to be achiral or not chiral, so to speak. Okay. So that discussion led us into looking at what are known as Fisher projections. And they are essentially a way of drawing chiral compounds. Basically based on, in a sense, skeletal idea, especially for the chiral carbons, or mainly for the chiral carbons, where we find the chiral carbons where lines intersect. So we use the idea of skeletal structures in Fisher projections to find where the chiral carbons essentially are. One other important thing to mention is that in a Fisher projection, the carbon chain is written vertically with the most highly oxidized group towards the top. And essentially, as I mentioned in the notes, when we talk about the most highly oxidized group, we essentially talk about the group that has the most carbon to oxygen bonds associated with it. Now, essentially, what I'm not going to have you do is I'm not going to have you take a structure and make it into a Fisher projection. I'm not going to ask you to do that. But what you do need to do is you do need to be able to draw an enantiomer of a Fisher projection. And specifically, what we're really going to ask you about, and we'll get to this, are for your monosaccharides. Now, before we get into the discussion of the monosaccharides, and then we'll include Fisher projections as well, let's, in terms of looking at a Fisher projection, okay, so the chiral carbon would be in the middle. And let's just say we had A to the top, B to the right, C to the bottom, D to the side, or D to the left, sorry. There are essentially two types of mirrors. There's the vertical, and there's the horizontal. Now, as you saw in the notes, when we use a vertical mirror, essentially everything that's vertical stays where it is. So here A and C would stay exactly where they are. B would go from the right to the left, and D would go from the left to the right. So with the vertical mirror, the horizontal groups switch. On the other hand, with the horizontal mirror, the vertical groups switch. So if we were going to apply, going back to our original structure, a horizontal mirror, D and B would stay exactly where they are. C would come from the bottom to the top. A would go from the top to the bottom. Now, as we talked about in the notes, which type of mirror is the one that's usually used? The mirror that's usually used, and basically for all the examples that are in the textbook and even really in the notes, is the vertical mirror. And as I mentioned, and I want to reiterate again, the reason why that is is because even if you were to use the horizontal mirror, the carbon chain would sort of flip. The top part of the chain would go to the bottom part would go to the top. So now that idea of writing the chain vertically would still be vertical, but now the most highly oxidized group would not be towards the top. The most highly oxidized group would be towards the bottom. And that essentially goes against how a Fisher projection should be usually drawn. So that's why, for all intents and purposes, it's the vertical mirror that's used rather than the horizontal mirror. So we're going to see that as we do our examples of monosaccharides in a few minutes. Okay. So with that being said, let's talk about our monosaccharides. So as we saw in the notes, the monosaccharides are the simplest carbohydrates. And essentially, they are the components of your disaccharides and your polysaccharides. If you got later on in the chapter yet, we're not going to really talk so much about polysaccharides, but we are going to talk about disaccharides. Your disaccharides are, composed of two monosaccharides linked together. Your polysaccharides are composed of many monosaccharides. And again, there's variation about how many is many, but essentially your polysaccharides are many monosaccharides linked together. That's really why the most of the chapter focuses on the monosaccharides, because their chemistry is so important and it applies in a lot of ways to the rest of the carbohydrates that you come across. So basically, a monosaccharide consists of the following. Number one, a chain of 3 to 6 carbons. And we saw the terms associated with that: triose, tetrose, pentose, hexose. So a chain of 3 to 6 carbons. One of the carbons is in a C double bond O group. And that led us to 2 different functional groups. Essentially, you can have monosaccharides that are classified as an aldose, which, as we saw, means that the carbonyl group is an aldehyde. So the C double bond O carbon is the first carbon in the chain. The other form for the C double bond O group that we had gives rise to what is known as a ketose. When we hear the term ketose, we should be thinking of ketone. And specifically what we find here for the monosaccharides is that the C double bond O carbon is the second carbon in the chain. I guess in theory, even with the aldehyde group, it could be at the bottom. But because, again, the most highly oxidized group is written towards the top, the aldehyde group really has to be the first carbon. It just turns out that for your ketoses, the C double bond O carbon is really in the same position. So it basically turns out to be the second carbon in the chain. Again, essentially, as the carbon chain is written vertically with the most highly oxidized group towards the top. And then finally, the rest of the carbons are attached to one OH group each. So that's really what you find for your monosaccharides: a chain of 3 to 6 carbons One of the carbons is in a C double bond O group, either an aldose, the C double bond O carbon is the first carbon in the chain, or a ketose. The C double bond O carbon is the second carbon in the chain. And then the rest of the carbons are attached to one OH group each. So essentially, using sort of aldose ketose terminology and the terminology for the length of the carbon chain really gives us all the information that we essentially need to classify a monosaccharide. So let's take a look at an example. Suppose we had the following Fisher projection. Okay, so the most highly oxidized group is towards the top, and the carbon chain is written vertically. Well, let's see, how many carbons do we have total? One, we can even number them really to help. 1, 2, 3, and 4. So we got a 4-carbon chain. So what terminology should come to mind? What terminology should come to mind would be a tetros. Now, in terms of the C double bond O group, what functionality does the C double bond O group here? The C double bond O group is an aldehyde. C double bond O with a hydrogen attached, of course, is an aldehyde. So what do we have here? We have here an aldo tetros. So this monosaccharide, based on the Fisher projection given, would be an aldo tetros. Now, in terms of finding the chiral carbons, we can assume in a sense that the chiral carbons in the Fisher projection would be where the lines intersect, carbon 2 and carbon 3 in this case. But in reality, you should be able to prove it to yourself. Just take carbon 2, for instance. What are the 4 things attached to carbon 2? OH, H, the top part, which is the aldehyde group, and then the entire bottom portion. Is that 4 different atoms or groups of atoms? And the answer is yes. Okay, so if you look at it further, which hopefully you'll take the time to do, you'll definitely see that carbons 2 and 3 are chiral. Now, to draw the enantiomer. Okay, as I mentioned, we're going to want to use a vertical mirror. So upon doing so, everything vertical is going to stay exactly where it is. So the carbon chain stays exactly where it is. Carbon 1 stays where it is, carbon 2 stays where it is, carbon 3 stays where it is, carbon 4 stays where it is. But now, everything that's horizontal switches sides. So for carbon 2, in the original structure, the OH was to the right and the H was to the left. In the mirror image, the OH is to the left and the H is to the right. And if you just wanted to draw it as OH, I'll make the assumption that that the bond is between the carbon and the oxygen. But for me, I like to clearly show the bond between the carbon and the oxygen. So that's why I like to draw it like this. Then for carbon 3, going back to the original structure on the left, the OH was to the left and the H was to the right. So now, in the mirror, the OH is going to be to the right, the H is going to be to the left. So that would be the enantiomer that would exist. Now, basically, their names, whatever their names are, and I don't know the names offhand, but one of the things I'll mention, which I'm pretty sure I mentioned in the lecture notes as well, but I'll mention here, is that you don't have to memorize the structures of the monosaccharides. So I'm not going to say draw D-glucose or D-galactose or stuff like that. You got to be able to problem solve like you saw in the notes, in the homework, in a sense, and what we're doing here and what we'll sort of do next week as well. But you don't have to memorize the structures of the monosaccharides. But basically, for these 2 structures, their names would almost be identical. So how do we distinguish between them? Well, the 2 enantiomers of a monosaccharide are essentially known as D and L. For the D enantiomer, the OH is to the right of the chiral carbon furthest from the C double bond O group. You know, in the notes, we started with, I believe, an aldo triose, where there was only one chiral carbon. But then we went into the example of an aldohexose, where you had multiple chiral carbons. And you could definitely have the OHs going in different directions. How would you distinguish one from the other? The way you would distinguish one from the other is, you know, essentially one enantiomer from the other is what I'm saying, is we need to be able to pinpoint one particular carbon and keep that consistent in a sense to look at. And the carbon that's been chosen to do that, essentially, and there's some other rationale to it, of course, as well, is that we look at the OH furthest on OH on the chiral carbon furthest from the C double bond O group. So if that OH is to the right of that chiral carbon, then you have the D enantiomer. For the L enantiomer, the OH is to the left of the chiral carbon furthest from the C double bond O group. So for these particular Fisher projections here, which carbon number are we going to be looking at? Carbon 4 is the carbon furthest from the C double bond O group, but it's not chiral because that carbon has two hydrogens attached to it. The one right above that carbon 3 is the chiral carbon furthest from the C double bond O group. So on the left here, what version do we have of this aldo tetrose? We have an L version because the OH is to the left of that particular chiral carbon. And on the right, what version do we have here? We have the D version because the OH is to the right of that particular chiral carbon. So one of the things you're going to have to definitely be able to do is to be able to draw the mirror images of the monosaccharides and be able to classify both of them as either the D version or the L version. That's something that you're going to absolutely have to be able to do. Okay. All right. So a lot of times we draw monosaccharides, or I should say sometimes, we draw monosaccharides as Fisher projections. But most of the time, carbohydrates exist as cyclic structures called what are known as Haworth structures. Well, why? You know, why don't they exist in an open chain form like a Fisher projection would indicate? You know, why monosaccharides, disaccharides, polysaccharides? Why do they exist in these cyclic or ring structures? Of course, when we say cyclic, we're referring to ring. Why do they exist in these structures? Well, it turns out that when you have a C double bond O group and an OH group in the same compound, they can react with each other. We saw a little bit about that. So let's talk about that a little bit further. As we know, the carbon of a C double bond O group has a partial positive charge associated with it. Oxygen, we don't really draw it in so much, but when oxygen has two bonds, and we've really only seen oxygen, well, shouldn't say that. We've seen oxygen with one bond. When oxygen has two bonds, it actually also has two lone pairs of electrons. Lone pairs are pairs of electrons on an atom that are not involved in chemical bonding. When oxygen actually has one bond, even though we didn't draw it in, that oxygen actually also has three lone pairs associated with it. When you have a C double bond O and an OH in the same compound, the oxygen of the OH can use a pair of electrons to form a bond to the C double bond O carbon. Now, if you think about it, when that happens, if you start with the C double bond O carbon, in this example here, you would go 1, 2, 3, 4, 5 oxygen, and then back to the beginning. So what are we doing? We're going around in circles. In the world of organic chemistry, what is that? That's a ring structure. Now, here are essentially some of the critical changes. So let me number the carbons as 1, 2, 3, 4, and 5. And there's my oxygen. So you got 1, 2, 3, 4, 5. Okay. And there'll be some other bonds as well. We'll get into the shape in a second. Now, here are some of the important changes. When the oxygen forms a bond to the C double bond O carbon, so here's the oxygen, and I probably should use a different color. So let me just change colors a little bit. I'm good with colors. And color, let's go blue. So when that oxygen uses a pair of electrons to form a bond to that carbon, what has to happen is that the hydrogen on that oxygen has to come off. Because in reality, oxygen will not want to have 3 bonds in a final structure. It can have 1, it's okay with that, doesn't want 3. So what comes off is that hydrogen. Now, the other thing is that the double bond between carbon 1 and this oxygen in red can no longer be there. Because if it was, and I'll draw it in just for you to see, if we left it as is, this carbon would have 1, 2, 3, 4, 5 bonds. And as you know, that can absolutely not exist. So the double bond between that carbon and the oxygen has to become a single bond. And that oxygen ends up picking up a hydrogen. Now, if you want to say that this hydrogen ends up being this hydrogen there, I'm okay with it. It's not the case. Actually, it might be the case if we went through the mechanism of it, but in any event, whether it's the actual case or not, I'm okay with it, if it helps you make it clearer. So oxygen forms a bond to the C double bond O carbon, loses hydrogen. The double bond between the carbon and the oxygen has to become a single bond, and that oxygen picks up a hydrogen. That's essentially what would happen when you have a C double bond O and an OH in the same compound. All right. Now, let's talk a little bit more about rings. Okay. So it turns out that when you have carbon atoms in a ring, carbon atoms in a ring, you can't rotate. You know, when we talked about alkenes, right? We talked about the fact that if you have carbons in a single bond, you could hold one carbon still and rotate around the other carbon. And then when we talked about alkenes, we talked about if you held one carbon still, you couldn't rotate around the other carbon. That same aspect, the lack of rotation, is true for carbon atoms in a ring. The other part is that even though carbon rings, for the most part, are not truly planar, there's an aspect of them that sort of has a planar type feel to the discussion. And that's the fact that for each of the carbons in a ring, besides the bonds to the other ring carbons, they essentially each have one bond above the plane of the ring. And they each have one bond below the plane of the ring. See here and there. And this drawing, the way this is drawn right here, is actually a good three-dimensional representation of showing this aspect. In other words, the bonds, and I need to fill in one more bond right here, sorry, of the bonds going above the plane of the ring and below the plane of the ring. So that's why you've seen in the notes in the textbook, when we've drawn these Haworth structures, we've drawn the rings like this because when we draw them in this way, you know, it's pretty, in a sense, it's clearer, I guess, to show the bonds going above the plane of the ring and below the plane of the ring. And keep in mind that because you have lack of rotation, if there is something above the plane of the ring, it can't be rotated so that it ends up below the plane of the ring, and vice versa. The groups that are attached to the ring carbons, not the ring carbons themselves, but the groups that are attached to the ring carbons are stuck on the side that they're going to. Either it be above the plane, which I guess I would call, again, top side, or below the plane of the ring, which again, I probably would call bottom side, to keep with our terminology. Okay. So one of the key things we're going to ask you to do is to draw the alpha and beta anomers for either aldohexoses or ketohexoses. So let's look at an example so we can talk about the steps and some of the parts that are involved. And of course, I would have to give you the Fisher projection to at least get you started. Okay. So we talked about the fact that for your hexosis, whether it's an aldohexose or a ketohexose, the OH group on the chiral carbon furthest from the C double bond O group is going to be the one to react with the C double bond O carbon to form the ring. So in this case, if I were to number the carbons starting from the top, the chiral carbon furthest from the C double bond O group is not carbon 6, it's carbon 5. So it's this particular OH group right here that's going to be used to form the ring. We'll get into that in a moment. The first step is to take the Fisher projection and turn it 90 degrees clockwise. And when you do so, you end up redrawing it from right to left. if you think about the aldehyde group at 12 o'clock, if you turn it 90 degrees, the tip of the pencil, the Apple Pencil, if you turn it 90 degrees clockwise, and I'm probably doing it the opposite direction in the camera, but if you think about the clock, if you're at 12 o'clock and you go 90 degrees clockwise, you end up to the right, 3 o'clock. So that's why we draw the C double bond O group furthest to the right. The key thing about this step is the locations of the OH and H on the chiral carbons. And the reason why this is so important is that if you think about the different, let's say, aldohexoses, which include glucose, galactose, mannose, this compound here, which I believe is gulose, and others as well. What's the difference between them? The difference between them are the directions of the OH groups on the chiral carbons. Somewhere, there's got to be a difference. In the notes when we did glucose and galactose, there was only one difference. In one structure, one of the OHs, and I should know it off the top of my head, but of course, I'm going to forget it now. I forget if it's 3. It's either 3 or 4. I forget which one it is. But for one of them, that OH is to the right in that group of 2, 3, 4, and 5. For the other one, that OH on that same carbon is to the left. I think it's carbon 4 is the difference, if I remember right. But that singular difference is the difference between glucose and galactose. So the reason why this step is so important is because when you go from a Fischer projection to a Haworth structure, there's essentially a defined relationship, a defined translation from left, right on the chiral carbons to what are going to be up and down on the chiral carbons, because they're going to become part of a ring. Now, as we'll talk about, and as you saw, there's sort of one exception to this, and that's going to be with the OH group on the last chiral carbon. So if we turn 90 degrees clockwise, if you're on the left, 9 o'clock, you end up at 12 o'clock on the top. If you're to the right, 3 o'clock, and we go 90 degrees clockwise, you end up on the bottom, 6 o'clock. So for carbons 2 and 3, the OHs were on the right. After we turn it, the OHs are going to be on the bottom. For carbon 4, the OH is to the left. After we turn it, the OH is going to be to the top. And for carbon 5, the OH is to the right. After we turn it, the OH is going to be on the bottom. And then after that, I would fill in the hydrogens on those carbons as well. All right. So that translation from left to right, left and right in the Fischer projection to eventually what would be top and bottom in the Haworth projection is very important. And this first step allows you to make that correct translation. Okay. Next thing, let's determine the ring size. And as we saw in the notes, there are going to be 2 different size rings we're going to come across. We're going to come across 6 atom rings. We're going to come across 5 atom rings. How do you figure out what ring size you're dealing with? Start with the C double bond O carbon, include all the chiral carbons after that, and include the oxygen of the OH on the last chiral carbon. So how many atoms does that give us total here? It gives us 1, 2, 3, 4, 5, 6. So what type of shape am I going to draw? I'm going to draw a hexagon. The way I'm going to start that is I'm going to put the C double bond O carbon furthest to the right. And then from there, I'm going to go clockwise. And for now, I would put in carbons 1, 2, 3, 4, and 5. Now, for carbons 2, 3, and 4, the way I'm going to fill in the 2 other bonds for each of them is I'm going to go back to my picture where the Fischer projection was horizontal and fill them in like I have it. So for carbon 2, OH down, H up. Carbon 3, OH down, H up. Carbon 4, H down, OH up. Now, carbon 5. So let's draw in the bonds. And there would be one to the right as well. And let me just move that hydrogen on carbon 3 a little bit. Make that a little smaller. And let's make that clearer because I don't want you to think there's a double bond. Okay, there we go.
I am so lost on this. I don't know if you could go a little slower, redo it,
Okay,
redo another one.
I'll redo it. I'll start from the beginning.
Okay, thank you.
Of course. So, first thing to mention here is that when we want to figure out which OH group is going to be the one that is going to react with the C double bond O carbon, it's the one that's furthest from the C double bond O group. So what we figure out is that the chiral carbon furthest from the C double bond O group is carbon 5. And we're going to see, and we're starting to see, that it's going to be this oxygen of this OH that's going to form a bond to the C double bond O carbon. So the first step in the process is to take the Fisher projection and turn it 90 degrees clockwise, and to draw it from right to left. Now, essentially, when we turn 90 degrees clockwise, think about a clock. If you're at 12 o'clock at the top, you're going to end up to the right, 3 o'clock. The most important part of this step are the directions of the OH and H's on the chiral carbons. Because when you go from a Fisher projection to a Haworth structure, there is a direct translation between right and left on the chiral carbons and top and bottom on the chiral carbons in the Haworth structure. OHs to the right should end up on the bottom, Fisher to Haworth. OHs on the left should end up at the top, Fisher to Haworth. By turning this 90 degrees clockwise, it allows you to set it up as such. So for carbons 2 and 3, the OHs are to the right. After I turn it, the OHs are going to be going in what direction? Down. For carbon 4, the OHs to the left. After I turn it, the OH is going to be going in what direction? Up. And then for carbon 5, the OH is to the right. After I turn it, the OH is going to be going in what direction? Down. And carbon 6 is not chiral, so I'm not worried about up or down or anything. But since it's at the bottom and I turn it 90 degrees clockwise, it ends up at essentially 9 o'clock. So that's step 1. Step 2 would be to figure out the ring size, because there's 2 different size rings that we could draw in a sense, or that we're going to come across or came across. A 5-atom ring and a 6-atom ring. So how do you figure out ring size? You start with the C double bond O carbon. You include all the chiral carbons after that, and you use the oxygen, because this is the oxygen that's going to form a bond to the C double bond O carbon. This is the oxygen that you're going to include in the ring structure. So how many atoms is that total? It's 1, 2, 3, 4, 5, and 6. So what does that tell me? What shape am I going to draw? I'm going to draw a hexagon. Now, how do you draw it? You start with the C double bond O carbon furthest to the right, and you fill in the rest of the chiral carbons going clockwise. For carbons 2, 3, and 4, not the last chiral carbon, but the rest of them, you go back and look at this picture here, and you fill in up and down off of these carbons, just like you have it here. And that's where we were up until this point.
Okay, thank you.
Okay. Okay, so the last chiral carbon, carbon 5. Based on this picture here, we would fill in the OH to the bottom, the H to the top, OH to the bottom, H to the top, and then CH2OH to the right. The problem is that it's going to be the OH that would be down here that would have to bond to form a ring with carbon 1. That positioning would actually provide too much of a what's called strain. And the easiest way to explain it is that if I put the OH here and I want to connect that oxygen to the ring, to the C double bond O carbon, I don't get a hexagon. Sometimes I describe it more like the baby carriage, and I'll draw it on the side so you can see if I can get my eraser. Let's get that off. So if I was going to put the oxygen, and I'll just draw it to the side here. So if we had 1, 2, 3, 4, 5, oxygen, and then back to carbon 1, you don't have a geometrically accurate hexagon. And therefore, that's not going to take place. You wouldn't get a ring that looks like that. So what happens? Before the ring forms, essentially, there's rotation around carbon 5. Now, I did say that you can't rotate around the carbons in a ring. I'm not changing my story. You can't rotate around the carbons in a ring. But right now, the ring hasn't formed. So in theory, I can still rotate around any of the carbons. The nice part about the rotation that we'll show you in a moment is that the positioning is consistent from example to example. What does it always end up with? Well, carbon 6 always ends up to the top. Hydrogen always ends up to the bottom. And the OH always ends up to the right. For the last chiral carbon, whether it's a 5-atom ring or a 6-atom ring, that rotation is consistent. So basically, you can just fill it in as such. Okay. The one thing I would probably leave out, which I'm about to erase, is the hydrogen on this oxygen here. Why? Because as we talked about a couple slides ago, now we're going to form the ring by bonding the oxygen on the last chiral carbon to the C double bond O carbon. As we talked about, what has to come off that oxygen in order for that to occur? The hydrogen. So this hydrogen here, which would be here, is not going to be there when the ring forms. Now, where does that hydrogen essentially end up? Well, we talked about the fact that you can consider that hydrogen ending up on the former C double bond O oxygen. So the last part of this is that we have to fill in the rest of what's attached to carbon 1. Carbon 1 has a hydrogen, and we know that the C double bond O can no longer exist. As we saw, what happens to the C double bond O? You get a single bond to OH. But here's the trick. There are actually two distinct possibilities. And I'm just going to erase, sorry. Just going to erase this part. There are two distinct possibilities for where that OH could end up. And I'll explain why in a moment. What I'm drawing is I'm basically redrawing the entire structure that I have on the left. And essentially, there's going to be one difference. When the oxygen forms a bond to the C double bond O carbon, now you have your ring. So for carbon 1, besides the bond to the oxygen and the other ring carbon 2, it should have one bond up and one bond down. We talked about how the C double bond O oxygen is going to become OH. There's basically a 50-50 chance that the OH could end up going down, or the OH could end up going up. 50-50 chance. It's a new OH. Wasn't here in all of this other work previously. Wasn't here in the Fisher projection. There's no defined translation for it because prior to the ring forming, it didn't exist. Why do these both exist? Because if this ends up on the bottom, could I hold carbon 2 still and rotate carbon 1 so that it ends up to the top? I can't. I can't rotate around the carbons in a ring. So because you have a 50-50 chance, you actually end up with two different versions. The relationship between these two structures is that they are anomers of each other. The alpha anomer has the OH going down off of, and actually, you know what, off of, that's okay, of the former C double bondo carbon. Okay. So for the alpha anomer, it has the OH going down off of the former C double bondo carbon. So the structure on the left, here's the former C double bondo carbon. Here's the OH going in the downwards direction, and therefore this is an alpha anomer. If you wanted to write the word alpha, it's fine, but a lot of times the Greek symbol is used. On the other hand, the beta anomer has the OH going up off the former C double bondo carbon. So in the structure to the right, again, carbon 1 is still the former C double bondo carbon. Here, the OH is going up, and therefore, this would be the beta anomer. And essentially for a monosaccharide, every time you take a Fisher projection and make it into a ring, you actually don't get one ring structure, you get two. They're identical. They should have drawn these identical. They're identical except for the new OH group on the former C double bondo carbon. If it's going down, you have the alpha anomer. If it's going up, you have the beta anomer. Okay. So, if you find other structures of aldohexoses and ketohexoses, and Fisher projections of them, and you can find them. I think they're even listed. I think there's a table in the textbook. Let me just take a quick peek. I don't know if they still have that table anymore. They used to. Yeah, they used to give you a table of all the different monosaccharides. Doesn't look like they do that much anymore, unfortunately. But if you, Google monosaccharides and you find the aldohexoses especially, you can practice drawing the Howard structures following the steps that are here. And probably to start next week's session, before we get to the rest of carbohydrate stuff, we'll probably do one more example to start, just to see if everybody's coming along with it. All right. All right. All right. So we are basically out of time for this evening. Does anybody have any questions before we say good night for this evening?
Yes, I have a question.
Sure.
So to differentiate between both the alpha and the beta, it's the OH. It's where that OH on the original COO
Yes.
carbon,
Yes.
not the other OHs, just that.
Yes. So one of the things that we'll talk a little bit about next time is that when you look at a ring structure, whether it's a 5-atom ring or a 6-atom ring, the carbon to the right of the oxygen is what is known as essentially the anomeric carbon. Because when these rings form, that's the carbon that has the new OH group attached to it. So one of the things that you want to become accustomed to, and again, we'll talk about this a little bit more next time as well, is that whether it's a 5-atom ring or a 6-atom ring, in the ring, the carbon to the right of the oxygen is the anomeric carbon. It's the OH direction off of this carbon tells us alpha or beta. So, and what that carbon is that's the former C double bond O carbon. Whether you started with an aldohexose or a ketohexose, that's the former C double bond O carbon. So maybe we want to try to remember it that way to help us as well. But honestly, it's no other carbon tells us alpha beta. So you can basically ignore the rest. It's that carbon to the right of the oxygen that tells us alpha beta. And as we'll talk about next time, it will also tell us whether we have a reducing sugar or not.
Thank you.
You're welcome. Of course. Other questions? Okay. So I know next Thursday the college is technically closed, but just for consistency, next Thursday night, especially because the exam is the Tuesday after that on the 16th, we'll have a Zoom office hour. Again, it's optional, so for whatever reason you can't make it, I'll post the video by the next day. Plan for next Thursday is to continue with the discussion of carbohydrates. And then if there's any additional time, I can answer questions or address maybe one or two topics that I hadn't had a chance to go over. All right. So start working on the carbohydrate homework. Go over the mistakes that were made in the chapter 12 and chapter 14 homeworks. Really start learning the reactions. I've stressed it's a major part. So you really want to start committing those to memory as well. Okay. All right.
Thank you.
You're welcome. Stay well,
You too.
and we'll talk to everybody soon.